in this problem we have been given a U-tube, and the U-tube has a slightly strange shape. This particular angle over here is given to be theta 1, while the angle on the other side is theta 2. There is no relationship given between theta 1 and theta 2, so we can assume that they are arbitrary angles. There is a liquid, this one, which partially fills the U-tube, and the density of the liquid is given to be rho. The mass of the liquid is given to be m. The cross-sectional area of the U-tube is given to be A. Now by the cross-sectional area is meant the area which is measured in this direction, that is the area which is perpendicular to the length of the U-tube. So for example, if I consider this area is given to be A, or on the other side if I consider this area, or even the area at the top like this, so this area is A. It's important to understand the orientation of the cross-sectional area A. For example, the surface of the liquid is going to be horizontal. So if you find out what is the area of the top surface of the liquid in the right hand side arm, this is not going to be A. It's not equal to A. So please be careful to distinguish between the area of the top surface of the liquid on the one hand and the area of cross section of the U-tube on the other. The liquid is now disturbed slightly, and therefore it oscillates in the U-tube like this, in this particular direction. So for example, in the right hand side, this surface over here would be going up and down the respective arm of the U-tube, and likewise in the left hand side it would be going down. It goes down when on the other side the liquid surface goes up, and when on the other side, that is on the right hand side, the liquid surface comes down, this would go up. But all of the time the surface, the top surface of the liquid in either arm of the tube, what I mean is this one, it's going to remain horizontal. So even if it is displaced, the new picture would be like this if it goes up, and if it goes down, the new picture is like this. And the same thing happens on the right hand side. So when the liquid oscillates or moves up and down in the respective arms, we have to find what is the time period of these oscillations. Now to solve this question, we need to know one small geometrical fact. Everybody knows that if you've got a cylinder, a solid cylinder, and let's say that the area of cross section is A and the height is equal to h, then the volume of the cylinder is obviously equal to A into h. Now what happens if the cylinder is I just distort it a bit. I have inclined sides like this. That is, the curved surface of the cylinder is not perpendicular to the base. You could imagine that you take circular discs. How would you build this? So an approximation of this particular figure would be, you take one circular disc and below it you place another but slightly displaced towards the left, let's say like that, and then the other one is slightly, the next one is slightly displaced further to the left, something like this. So in cross section it would look like this, not in cross section, from the side view would look like this, 1, 2 and 3 and 4. So this begins to look like this particular inclined cylinder, and as you decrease this particular overhanging portion, it looks more and more like that cylinder. So that's what I mean by drawing this particular cylinder. So if you look at the side view of this cylinder, it would appear to be something like this. Yes, it would be a parallelogram, and the top and the bottom sides are shown to be horizontal because this area and this area is horizontal. Now I want to develop a formula to find the volume of this particular inclined cylinder, and the way to do that is to imagine that what I'll do first is I'll draw a disc. In the original picture it's like this actually. So that's the cross section. It's perpendicular to the sides. It doesn't look perpendicular, I think. This angle is 90 degrees and this angle is also 90 degrees. And likewise I'll draw a perpendicular cross section over here. I'll try to draw this a bit better. What I've got now, this thing is a proper cylinder, what we usually call a cylinder. So all this explanation is just to understand the meaning of this particular geometrical construction. Right. Now this construction is going to help us to evaluate or to find a formula for the volume of this particular inclined cylinder. So the first thing I do is to cut out this part of the inclined cylinder. So this thing I'll remove it and I'll stick it to the bottom. So you have to use your imagination. When I stick it to the bottom like this, what happens is the top part, it just disappears. So I'll just remove that like that, and what has happened is the top part has gone to the bottom. Now in doing so I have not actually changed the volume of the original inclined cylinder. However, I have changed the shape. It has now become a proper cylinder, and you know that the area of a proper cylinder is given by this formula. So if this area, that is the cross sectional area, is given to be A, so by that I mean, what is the cross sectional area of an inclined cylinder? We mean this area, or even this area, or this area. The area which is perpendicular to the length, to the sides, that's going to be the cross sectional area. So this A, when I multiply it by this length, which in the original picture it corresponds to this length. Now that's not the height. Usually the height would be, you would call this the height. So you could call it the slant height. So the slant height or the inclined height of the cylinder is this. I'll give it a symbol S, and A is the cross sectional area of the inclined cylinder. So of course the volume is going to be given by the cross sectional area multiplied by the slant height. So just to recap, I've got an inclined cylinder like this, and the slant height, this one or even this one, they are both equal of course, that's equal to S, and the cross section, now this is not the cross section, the cross section would be this sort of thing, something like that. So if the cross sectional area is given to be A, then the product of the cross sectional area and the slant height gives me the volume of this particular inclined cylinder. And why am I concerned about calculating the volumes of such inclined cylinders is that there is going to be, you can easily see that if you go to the original figure, then just imagine the top. surface of the liquid in the right hand side, and if I draw a plane through some arbitrary part of the right hand side, it's going to describe the bottom end of this particular inclined cylinder, and we will be calculating the volume of such an inclined cylinder. The inclined cylinder is made of the liquid, of course. The formula, of course, which we will be using is the one that we have just developed right now. It is the slant height, this one, S, multiplied by the cross-sectional area, which is not the area of the top, but it's the area of a perpendicular cross section. So this area A multiplied by this slant height S is going to give you the volume of this particular inclined cylinder. Now if we imagine the oscillations of the liquid inside the U-tube, you realize that the oscillations are neither going to be linear SHM nor are they going to be angular SHM, because if they were linear oscillations, or if the motion was linear SHM, then all particles would be moving similarly along a straight line. They would be vibrating parallel to the same straight line. For example, if we consider a particle over here, then this particle, it does seem to be oscillating parallel to the right hand side branch of the U-tube. On the other hand, if I have a particle in the left hand side branch, then it will be moving in this direction, vibrating along an entirely different line. And if I have a particle somewhere over here, then the particle would not be even vibrating along a line, it would be moving along a curve. Vibrations, no doubt, but these would be curvilinear vibrations. So it's neither linear nor is it angular. When angular SHM, when you have angular SHM, the particle moves along a circular arc. Or if you have a body undergoing angular SHM, then the body rotates back and forth like this along a circular arc. Now that's not the case, obviously. So the liquid neither has linear oscillations nor does it have angular oscillations. And we have seen in class that whenever you have oscillations which neither can be classified as linear nor as angular, then a very safe way to attempt the problem is to do it by the conservation of energy rather than by applying F is equal to ma. We will assume in this problem that friction or viscosity is the equivalent of friction when it comes to liquids. These things are absent, and because of that we can assume that the total mechanical energy is conserved. In other words, the kinetic energy of the liquid plus the potential energy of the liquid that never changes from some constant value. Now just imagine that the liquid has been set into oscillations, and during the course of its oscillations you consider a snapshot of the oscillations when the liquid in the right hand side arm has reached this level, and correspondingly the liquid in the left hand side arm has descended to this level. So just to clarify the exact position of the liquid, I'll just shade it in a different color. We are looking at the liquid, a snapshot of the liquid, and the liquid is actually this one, right? So the original level of the liquid in the right hand side arm in equilibrium is this, that's the equilibrium level, and in the left hand side arm the equilibrium level is this. So in the left hand side arm the liquid level has descended compared to the equilibrium level, and in the right hand side arm it has ascended. And we are going to assume that in this arbitrary position of the liquid, all liquid molecules, all liquid particles move at the same speed. They may be moving in different directions, but during the course of the oscillations, right and left, all particles move with the same speed, and that speed, if it's v, then the total kinetic energy contained in the liquid in this particular snapshot is half mv square. Now let's consider the potential energy. For the potential energy, we first have to define what is the zero reference or the datum of the potential energy, and we'll assume that the equilibrium position of the liquid corresponds to the datum of potential energy. In other words, when the liquid level was over here in the left arm, and correspondingly the liquid level was the same in the right arm, in equilibrium the levels of the liquid will be the same. I can even draw a line indicating this fact. So the zero of the potential energy corresponds to the position of the liquid when it is between these two levels. And we now have to just find what is the change in the potential energy as compared to the equilibrium position, and this change in potential energy will now give us the absolute potential energy, because we are comparing it with the situation corresponding to the datum. So we start with zero potential energy, right? Now effectively what has happened is, when the liquid has moved towards the right hand side branch, effectively what has happened is this volume of liquid has actually got transferred over here. So that's the only effective change that has happened during this motion, and we can use this to find what is the change in the potential energy. The first thing we notice is that the mass of this left hand side region, which I have shaded in purple, that much amount of liquid, it must be the same as the mass of the shaded purple region in the right hand side, and therefore the volume must also be the same. So what would be the mass of that particular part of the liquid which has got transferred from left to right? The mass would be the volume of that purple shaded liquid multiplied by the density, which is rho. And the volume, of course, that's why we spend so much of time in deriving a formula. The volume is the cross sectional area A. Remember, I'm talking about this area and this area. That sort of area is the cross sectional area, that's given to be A, multiplied by the slant side, so, or the slant height, this if I call it S, so multiplied by S, multiplied by rho. So A multiplied by S multiplied by rho is the mass of this particular volume of liquid, and it must necessarily be equal to the mass of this particular liquid also. But the mass of the liquid, the purple shaded liquid in the right hand side, you can evaluate it independently by using a similar formula. So it is the cross sectional area A multiplied by Now the slant side is of course this one, which I'll call S dash. So multiplied by S dash multiplied by rho. But the masses are equal, so AS dash rho must equal AS rho. So obviously it means that the two slant sides S and S dash, they must be equal. In other words, what I mean is this slant height is also equal to S. Now the change in the potential energy when this purple shaded liquid goes from the left side to the right side can be calculated as follows. Delta PE is equal to, now remember we are talking about the final potential energy minus the initial potential energy, and we have started from the datum position, so we are just talking about the final potential energy because the initial potential energy is equal to 0. So in other words, we are trying to develop a formula for the absolute potential energy by considering the change in the potential energy. So what is it equal to? It's equal to the mass of that purple shaded liquid, which of course I'm going to use this formula for, multiplied by G and multiplied by the change in the height of the CM of the purple shaded liquid. Now to find delta HCM, I'll draw a slightly enlarged version of a part of the diagram. See, this is the liquid which is shaded in purple in the original diagram, so I'll shade it in purple in this diagram also, and that's transferred to the right hand side above this level, and it appears to be something like that. So I'll shade that also in purple just to tell you clearly what I'm talking about. Now the original position of the CM is over here, right? Now let's try to calculate the distance of the CM, the perpendicular distance of the CM from this dotted line. Now this angle is given to be theta 1 and this is equal to S. So obviously this entire height of the inclined cylinder, that's going to be S multiplied by sine theta 1, and clearly the distance between the dotted line, that is the top of the inclined cylinder, and the CM is at the geometrical center, so this distance must be half into S into sine of theta 1. So that tells you how much below the dotted line is the CM originally. Now what happens is this liquid, effectively it goes to the right, and the CM also moves therefore to the right. To the right, I mean it goes over here. The CM is now over here, and we want to find now what is the distance of the CM above the dotted line. So if we do it in the same way, this distance is going to be half into S. Remember, the slant height of both of these inclined cylinders is the same, S, and multiplied by, this time the angle is different, this is theta 2, so it's going to be sine theta 2. In other words, delta HCM is the sum of half S sine theta 1 and half S sine theta 2. Let me substitute. The potential energy of the liquid is equal to, now mass is A times S times rho, G multiplied by, I'm going to add half S sine theta 1 and half S sine theta 2, so I'll take half S common, into sine of theta 1 plus sine of theta 2. That's the potential energy. Right. Now the kinetic energy is half mv square. So this potential energy term, I have to actually substitute it over here. and the addition is going to be a constant. So let me just write it instead over here itself at the bottom. So this is the potential energy. Now I'll write KPE plus KE equals A multiplied by S into rho G half S into that bracket plus half into total mass times the common speed square, and that's equal to a constant. Now as usual I differentiate this with respect to time, so I'll just collect the common terms, the constant terms together. So A is a constant, rho is a constant, G is a constant, half is a constant, sine theta 1 plus sine theta 2 is a constant. Now what that actually means is only S multiplied by S, this S and this S, so S square remains. And remember, S is a variable. If you go to this, you'll see that as the liquid, if you go to the original diagram, as the liquid oscillates left and right, this S is going to change with respect to time, and so is this S. So it's a variable. So its derivative of S square, it is actually, is going to be 2S multiplied by ds by dt. So ds by dt, if you go to the diagram, would be the rate of change of this length. Or alternatively, I could consider a number line like this, like the x-axis, or I'll call it the s-axis, and the 0 of this s-axis would be over here, and the value of s would actually tell me the position of the top surface of the liquid. So for example, let's see, this distance is s, of course. Well, it's not really distance, it's the coordinate. So for example, if the top surface during the course of its oscillations, it goes below the equilibrium position like this, then the corresponding value of s would be read out that way. So this would be the coordinate and it would be negative. So in short, s would tell us the coordinate of the top surface of the liquid in the right hand side, and therefore ds by dt would be the velocity of that liquid. So this ds by dt in the equation which I've just written, I'll just cancel ds by dt and write it as v, the velocity, plus half into m. Now remember, this v over here, I called it the speed initially, but in the formula half mv square, this v could also be taken to be the velocity, because the velocity, according to the way that I've just defined it, is ds by dt. It could be positive or it could be negative. It's a scalar, a positive or a negative number. We are treating it as a scalar rather. It's actually a vector. But since we are treating it as a positive or a negative scalar, its square is always going to be a non-zero. So essentially, in the way that we have defined the velocity of the topmost surface, there is no difference between the velocity square and the speed square. So now I will change my definition of this v. I'll be calling it the velocity. So in the differentiation process, I get multiplied by 2v into dv by dt is equal to 0. Now this velocity, of course, appears twice. It's going to cancel this velocity and this velocity, and it's just a matter of manipulation. See, this m is the total mass of the liquid, whereas the m which we wrote as as rho is the mass only of the liquid which has effectively been displaced. So in the diagram, the mass of the purple shaded liquid. Now just simplify all this. So the first thing I will do, I'll cancel this 2 of course, and this 2 will also go with this 2, and this, the second term I'll write it as m multiplied by d2s by dt square. So dv by dt can be written this way, and then these two terms I combine together with some manipulation. So I'll divide by m. So I'll write the second term first. I'll get d2s by dt square. Remember, I have divided by the total mass, so that must come in the denominator, 1 upon m of, now I'll write this term, all the constants first. So a rho g sine theta 1 plus sine theta 2 into s is equal to 0. And immediately you compare it with our standard SHM differential equation, which is d2x by dt square plus omega square x is equal to 0, and you realize that the top of the liquid in the right hand side column actually has linear SHM. In fact, it's true for even the top of the liquid in the left hand side column, but we just consider one of them right now. So it has SHM, and we can easily see that its omega, the omega of the SHM of the top surface of the right hand side column liquid, is going to be the square root of this number, and therefore the time period of the SHM is 2 pi upon the square root of that number. So it's 2 pi multiplied by square root of the total mass of the liquid divided by area of cross section into density into gravitational acceleration times sine of theta 1 plus sine of theta 2. So what have we done? We have found the time period of oscillation of the top surface of the liquid in the right hand side column. It's going up and down like that with this time period. Now obviously that's going to match the time period of oscillation of any particle in the liquid. The particles may be oscillating along different paths. The bottommost particle would be oscillating along this path, for example. But the time periods must be the same, and they will be identical to what we have just now calculated.